Hi guys, hello once again. So let's continue with our lecture today on classical computation and Turing machines. So today I want to talk to you about several new concepts involving the notion of a Turing machine. And okay, let me just remind you that in the last class we ended up stating the Church Turing thesis, which basically says that any algorithm can be realized by a Turing machine. That's the thesis. Okay. So Turing machines are this collection of objects that we discussed last time, right? So there's an alphabet, there's an external alphabet, there's an internal alphabet. There is there's a tape with a head, right? And this head computes a certain transition function. There's a set of states, there's an initial state, and there's a halting state. So these are all things that you're going to remember from the last lecture that a Turing machine has, right? And we've seen that for every algorithm, we have a different Turing machine, okay? Now, the Turing machine, say a Turing machine M, can be encoded. It's finite, right? So it's a bunch of sets, and whatever it is, it can be encoded in a string because it's finite. So you can attribute a number to it. So I can associate to a given Turing machine a string, which I'm going to denote by brackets on M. Okay. The input of the Turing machine, call it X, is also a string. Okay. Input string. Right. Now, there is this concept of a universal Turing machine. Which basically says that there is a Turing machine U, which takes as an input the string on which the Turing machine that we want to represent is encoded. It takes an input string and it gives me the Turing machine associated to M applied on input X, right? So this is the concept of a universal Turing machine. So it's a sort of emulator. It's like a software, right? So you have the computer, which is U. It's universal because it can emulate any Turing machine you want. And you have a software, which is this string, this finite string that codes the Turing machine that we want to be emulated. And it takes both the string that codifies the Turing machine, and it takes an input string, and it gives me as an output the function of the machine M evaluated on X. Okay. Now, because Turing machines are algorithmic things, okay, the Church-Turing thesis guarantees that there is a universal Turing machine. There exists a universal Turing machine. This is universal Turing machine, okay? Because we can describe what the Turing machine does in terms of an algorithm, and any algorithm can be realized by a Turing machine because of the Church-Turing thesis, which is a thesis, not a theorem, that kind of guarantees that there is such thing as a universal Turing machine. Okay. So today I wanted to introduce this concept of a universal Turing machine. And I also wanted to give you some examples of Turing machines. So here's an example, a very simple one, not very useful also. So what you see here is a starting tape with a value written on it and the head alpha. Alpha is the state of the Turing machine. And the transition rules are such that if alpha is, the state is alpha, and it reads, the Turing machine head reads bit 0, then it changes to bit 1, moves to the right, and changes to state beta. Now we have to look what happens when the machine is in a state beta. It sees a bit 0. This is given by this line here. It just writes 1 instead of 0. It erases the 0 and writes a 1, goes to the right, and goes to state alpha. This is what it does. Okay? Now, if it's in state alpha and it sees bit 1, it says halt, goes to the halting state. So this Turing machine just changes this string of bits 00010 to 01110. Now, all you have to do to come up with your own Turing machine is that you need to come up with an alphabet. In this case, the alphabet is just 0 and 1. You need to come up with these transition rules, which tell whether, depending on one state or another, whether the machine goes to the right or goes to the left. And you have to define a halting state. Okay. So this is given by these transition rules here. So this is a concrete example of a Turing machine. It's a very simple one. It doesn't do much, but it's a Turing machine nevertheless, right? I took it from a paper by Bennett on thermodynamics of computation. Is a 1981 or 1982 paper. I can't remember exactly. And it's very, very nice. I'm going to send it to you on the today's papers so that you can have a careful look at it. It's a pretty interesting thing. Now, here's another example of a Turing machine. So I've taken this from this Stanford website here. You can go and check it out for yourselves. So this is a machine that computes the sum of two numbers. Now, I'm not going to go through the details of this, but I just felt that it would be nice to give you the idea behind it, right? So just to exhibit the machine. So these are the states, okay? There are 5 states. Now, what this means is that if this is coded in such a way that in the parentheses you get what you read in the string, okay, and then the action. So this says if you read 1, just move to the right. Okay. Now, when you go here, from when you see 1, you move to the right, and you come back, remain on state 0. Now, this means that if you keep seeing 1, you just keep moving to the right, but you remain on the same state. On the other hand, if you see 0, you just change it for a 1. You erase it and you write a 1. And then you move the machine to state S1. Okay. Now, if the machine goes on state S1 and sees a 1, it moves back to the left. Okay, but remains on state 1. And this goes on until the machine sees state 0, and then it goes to the right. 1 unit of space to the right. And so on and so forth. I think you get the idea, right? So this is a machine that if you actually work it out, you can maybe come up with an example. It will add numbers, okay? So this is taken from, once again, from this website here. If you want to work it out, you can work it out as an exercise. I leave it to you. It's a bit tedious, but it's straightforward, okay? Now, let's go a bit more into this idea of Turing machines. So what a Turing machine does is that it computes a function. This is the idea. So that means it takes an input x and it gives you as an output f of x, where f is some function. Of course, this is written on a tape and so on. I mean, we've seen how it works, right? What the Turing machine does is that it computes the function and writes the value of the function. For a given input tape, it writes the value of the function on the output tape. Okay. So this is the idea. Now you can ask the question, okay, let's see an example of a function that the Turing machine can compute. Okay, so one example would be x squared, right? Takes x and outputs x squared. Now it's intuitive that a Turing machine can do this. So say, for example, I write on a tape 1, 1, 1, and this represents number 3, right? I send this into my Turing machine. Okay. And now here, all this machine does is that for each one, I mean, it counts the number of states, and then it writes in unary 1, 2, 3. So 1, 1, 1. It computes x squared in unary, right? So we're gonna have 3, 1, 1, 1, 1, 1. So this is 1, 2, 3, 5, 6, 7, 8, 9, right? So all it has to do is that it has to count how many ones are here, and to compute x squared, it just writes for each one, it writes a string of the same size of ones on the output tape, right? So it's pretty clear, I mean, it's pretty intuitive that the Turing machine can do this, that this is a computable function, right? That you can compute it. It's pretty intuitive. Now, one can ask the question, is it true that a Turing machine, is it possible that a Turing machine MF can compute any function f, right? So this is a question whether for any function f, I can come up with a Turing machine that is capable of computing it, right? So this is an interesting question. So let's consider the following function. So this function will take two inputs. It will take the string associated to a Turing machine M. So this codifies the Turing machine M. And it will take an integer x. And it will associate me to a function of M x, which is going to be equal to 1 if M of x halts, zero otherwise. So what this says is that this is a function, right? It takes two numbers and it gives me either 0 or 1. And it's 1 if the Turing machine M associated to this number applied to input x stops. So if the computation halts at some point, and it's 0 otherwise. Okay. So what I want to prove now, the statement that I want to make, it's known as the halting problem. Is that this function f above is uncomputable in the Turing machine sense. It means that there is no Turing machine that can take as an input the number associated to a Turing machine and a given number and tell me whether that Turing machine will halt on that number. In other words, there is no algorithm to decide whether a Turing machine will halt on a given input or not. Okay. This is what I want to prove. Okay. So let's prove it. Okay. So suppose there is a Turing machine such that I'm going to call it B. B takes as an input the number associated to a Turing machine M and a number X, and it gives me 1 if M of X halts, and it gives me 0 otherwise. Okay. Now, consider another B function, B prime, another Turing machine, B prime, that simulates the work of B on input Y, Y. So this B prime will simulate what the Turing machine B will do on input Y, Y. Okay. And this B prime is such that it never stops, never halts. If BYY is equal to 1, and it halts otherwise. If BYY is equal to 0. Okay? So notice that we've just done something here. We've reversed the roles of never halt and halt. Okay? So whether before, if B was equal to 1, it would halt, B prime applied to Y will never halt if B applied to Y is 1, and it will halt if it's 0. Okay? So it's kind of reversed. So this B prime, this reverser, sometimes it's called, it will take an input Y, it will simulate within itself whatever B will do but now on input YY, and it will give me these results depending on whether the simulation came up such that BYY is 1 or whether it came up such that BYY is 0. Okay. That it never halts, it just means that it will just go infinitely to the left or to the right on the tape, and halt, it just means that it will stop whatever it was doing once it finds out BYY is 0. Okay. Now the question that we want to ask, let's see if I can. Is, does B prime halts for input B prime? So this is the question that I want to ask. Okay. So let's see what this does. Run out of space. Okay, let's see. Okay. Let's see. Like this, I can save and look at it later. There you go. We can keep this. We're not going to be needing this, and this we can take a new one. So, suppose it does halt. Right? That means if it halts, right? If B prime halts for input brackets B prime, that means that B equals 0 for input B prime, because that was the definition of B prime, right? It would halt if B evaluated on this input were 0. Okay. But B itself is 0 when B prime on input B prime never halts. So this is a contradiction, you see. So suppose that B prime on input brackets B prime halts, then this will happen for B equals 0 on this input, and B is 0 on this input if B prime on B prime never halted. So you see, we're in trouble. Now suppose it never halts. That means that B is equal 1 for the input B prime, which means this was going to happen by the definition of B. B would be 1 if the Turing machine associated to one of its input evaluated on the number of the other input, would halt. So we've constructed a situation in which if B prime halts on brackets B prime, then B prime never halts on brackets B prime. It's a contradiction. On the other hand, if it never halts, it halts. Okay? So the conclusion is that such a machine, such a function that decides whether a Turing machine stops on a given input or not, cannot exist, because if it does exist, we're led to a contradiction. So it's a proof by absurd. Okay. So this is called the halting problem. And it's one way of establishing the existence of a non-computable function. Okay. So an undecidable predicate, if you want. You can't decide whether a Turing machine, there's no algorithm that will let you decide whether a Turing machine halts on a given input. This is pretty cool. Okay. Now remember, we've mentioned earlier that the set of all Turing machines is countable. You can count them. Okay. This is just because Turing machine is a finite object made of finite sets. So I can attribute a finite number to it, right? Binary or whatever you want. While the set of functions from space A to A, so binary sequences, if I take the space of all binary strings to the space of all binary strings, this is an uncountable set. We've mentioned that. Okay, so this is another way of seeing that there must exist non-computable functions, because there are way more functions than there are Turing machines. Okay. But here's a different argument. Okay, that relies on the fact that Turing machines are countable. So the argument goes like this. It's called the diagonalization argument. And it's from the 1930s. I think due to Turing, I'm not sure. So since we can count Turing machines, we're going to enumerate them in the following way. So here I have 1, 2, 3, la da da, I, la da da, n. And of course, this will continue. Here I'm going to have Turing machine F1. Here I'm going to have Turing machine F2. Fi, Fn. Okay. Now, what I'm going to write here is F1 of 1. Here I'm going to write in the diagonal F2 evaluated on 2. Here Fi evaluated on I, and so on. And each one of these lines is going to be the value of the I function evaluated on this number here, corresponding to this column. So this is Fi of 1, this is Fi of 2, and so on and so forth. Okay. Now there's this diagonal here. And I'm going to construct a function d which takes an integer number and gives me another integer number. Okay. But I'm going to construct D such that when it's evaluated on the integer I, it's always different from F I evaluated on I. So the value of D, it's always different from these values here. So we're never gonna have one of these diagonals equals to D evaluated to the ith number. I can construct, this is a reasonable function, right? It takes a number and it gives me another number, just that this number is different from the ones here in this diagonal. Whatever the values are, I just construct the function. Okay, so this is true for all values of I. Now there's no doubt that this function exists, right? I can construct it, I just look at it and just add one or whatever, or change the value. Okay. Now, this function is not on the list. So these are all Turing machines, right? So these f's correspond to functions that are computable because they correspond to a Turing machine. This function here that I constructed, this di, is not on the list. And here's why. Suppose that it's equal to some fk here, whatever it is. Okay. Suppose it's equal to this fk. Well, it cannot be equals to fk because by construction, d evaluated on k is different from fk evaluated on k. This is very simple, you see? I've constructed this function so that it is different, so it cannot be any of these generic fk's here. So this is an uncomputable function. So this is a proof, this diagonal argument for the existence of non-computable functions. Okay. So the conclusion of all this is that there are functions which can never be computed, which are uncomputable by a Turing machine, by an algorithm for that matter. Okay. So this is very nice. It's pretty disturbing, right? If you want, you can read about these things. It's very nice. There's a lot about this in several books. I can pass you papers and everything. But this halting problem is kind of the mathematical analogous to Gödel's incompleteness theorem and to undecidable propositions in logic. Okay, so you can read about it in a lot of the references that then I can give it to you. But there's a lot of implications for mathematics. Now, the halting problem has a lot of connections with many problems in mathematics, which are undecidable or uncomputable. Okay, and I want to show you some examples. Now, I'm not going to go into the details of any of these, but just for your information. Okay. Last year, I visited MIT and I was walking around the corridors of the math department. And I stumbled upon this piece of paper here that was hanging on the wall, and I couldn't resist to take a picture. Now, I don't know who the owner is because it's not written on the paper, so I cannot give due credit. But if you want to know more about it, you have to go to MIT and go around the corridors and look for it. Well, I think it was somewhere on the second floor of the main building. I can't remember exactly, of the math department. But okay, this is the best I can do to locate the author. I don't know who he is, but it's very informative. So here it is. So this is the halting problem, okay, Turing 1936. And these are all mathematical problems which are connected to it, undecidable, okay, uncomputable. Okay. So if you want, if you're curious, you can go and look for them. Some of them are very interesting. Like for example, this Diophantine equations here. This is pretty nice. It's a very famous one of Hilbert's problems. So I'm gonna let you go and look for it. It's pretty nice. Let me just take my face out of here so that you can look at higher dimensional knot theory. There's references to the various authors that contributed to showing that these problems are related to the halting problem. Okay. So there are things which are uncomputable. Now, if things are among the realm of the computable, that doesn't mean that they can be computed in practice. Okay? So what I mean is that there is a hierarchy of problems. And this is what I want to introduce now, is this notion of complexity theory. Okay. So let's start by defining something which is called a polynomial growth. Once again, this is just so that you have a notion of it. We're interested in quantum computing, so just so that you know exactly what some things mean, but we're not going to go into the detail of any of it. So we say that a function has polynomial growth if this function evaluated on an integer n is always smaller or equal than a constant times m to the power d, okay, where n is in the large limit and c and d are constants. Okay. So if the function has polynomial growth, there's a notation that says that f is poly n. It's a polynomial in n, the growth rate. Okay, this is just notation. Okay. I also want to introduce a Boolean set, which is just this set here, 0 and 1. It's a bit value. Okay. So let's introduce the class P. So a function f on Boolean variables, so from the Boolean set to the Boolean set, is in class P. P stands for polynomial. If there exists a Turing machine that computes it in time Tn, which is polynomial, meaning that the growth of n, of t of n for large n is bounded by some polynomial function. So this is what it means to be in the class P. It's what you hear all the time. P, polynomial class. Okay. So if the Turing machine takes an input of size n, okay, this T of n, we've already seen it, is the number of time steps that the Turing machine takes to solve the problem for an input of given size n. If this is polynomial in n, then we say that the function f is in this class P. Okay. So analogously, we could define that the predicate f is in this polynomial class. If the Turing machine can decide to attribute 0 or 1 to this predicate in a polynomial number of steps, bounded by a polynomial. Okay. We can have a similar definition for space. It's a category or complexity class called P space. It's very similar to the P one, but instead of time is in space. So we're going to say that a function f is in P space if there exists a Turing machine such that computes f in Sn equals poly n steps. So that means that the Turing machine will visit Sn sites on the tape, and the number of sites as a function of the size of the input is bounded by a polynomial. So this is the definition of P space. Okay. Now it's kind of intuitive that the class P is contained in the class P space. So I'm not going to go into the details of what's contained in what and what classes are out there and so on. This is just so that you have the bare minimum to know what it means to be polynomial time and so on, so that we can later understand when I say that the quantum algorithm gives you a exponential advantage over the best known classical algorithm. I just wanted to understand what does it mean to say that it computes in a given number of steps in a bounded by a polynomial and so on and so forth. Okay. Now, of course, at this point, we can mention the class NP, non-polynomial. So these are predicates. This class is defined only for predicates. For which, if the answer is yes, it can be checked in polynomial time. So you see, there's more things here, because if you are in here, not necessarily there is an algorithm that gives you the answer to the problem in polynomial time, but if someone magically hands you the answer, then you can check whether the answer is correct or not in polynomial time. So this stands for non-polynomial. Okay? And I just want to say that one of the biggest open problems in mathematics is whether the class P is equal to NP. So this is an open problem in computer science and in mathematics, which has deep consequences and deep questions for mathematics and computer science and everything that we can compute and so on. So it's generally believed that they are different, okay? But nobody has managed to prove, right? Now, I brought you here a little drawing of the various complexity classes. Okay? So there's P space, NP, and P complete. We're not going to go into the details. Then there's P problems. So there's a hierarchy of complexity of problems, of predicates, okay, within the computable ones. All right. Now, I've argued at the beginning of the course that if your problem is not here in P, then there's not much hope to solve it in practice, right? Of course, it's computable and you can solve it, but if it's going to take an exponential number of steps in the input size, then, as we've argued, physics inputs limits, right? There's for a classical computer, I mean, you can't imagine the transistor size being much smaller than a hydrogen atom, or the computation time being much faster than the transition atomic rate of the hydrogen atom, for example, orders of magnitude, right? And we've seen that there are like really simple 1 million digit numbers that you can't factorize in terms of primes if there is no algorithm that can factorize in polynomial time. Okay, so this really tells you in practice what you're ever gonna be able to compute or not, even though all of these are computable functions that live here. Now, BQP is bounded error quantum polynomial time. I don't want to go into the details. I don't know if we're going to have time to look for it, but certainly in Praskill's notes that I recommend you to read, it's well explained and described. And yeah, maybe we'll talk about it later. Maybe we won't. I don't know yet. This will also depend on what you want to hear. But in principle, you already know what's P and NP and P space, and that's already something quite nice. If you want to go and have a look at the book of Scott Aronson, is also very nice because it's a semi-professional way of stating things, right? So he can explain in a very, very nice way. It's very clear, all these complexity classes, and someone who has training in science can easily understand it. With a little bit of effort, just read the book and get familiar with these things. And it's also very nice to read Scott's book. Okay, now I want to introduce this notion of circuits for a computation, okay, so that we can start to go in the direction of quantum computing. So it's the idea of Boolean circuits. So here's a function from the Boolean set Bn to the Boolean set B. So just to remind you, B is just 0, 1. All right. Now, a circuit just take here. So a circuit is just something that takes in my n bits and operates on them. For example, this one here. So these are n bits, which define this string here. And in the end, I get a bit out of my circuit. Now, these operations on the circuit define what my function f does. So all this here is going to be my function f. Okay. Now, we can speak about a basis for Boolean functions. Okay. And we can say that a basis is complete. I'm going to read from the book so that I don't say anything wrong. So we can say that a basis is complete if for any Boolean function f, there is a circuit over this basis. Let's write this down. A complete basis A if for any Boolean function f, there is a circuit over A, so using only the elements of A, that computes f. Okay. So A is a complete basis so A is complete. Sorry, sometimes the computer doesn't compute well. So A is a complete basis if for any Boolean function f, there is a circuit using the elements of A that computes f. Okay. So here's a complete basis. There's a theorem that you can prove. It says that the NOT gates, the OR, and the AND gates are sufficient to compute any Boolean function f. Okay. Now the proof is in Kitab's book, which I'm using. Okay, this is theorem 2.1, page 19, if you want to go and look. I'm not going to go over it, but just for your information, here is this basis, okay? This is the NOT gate, this is the OR gate and the AND gate and the truth tables. Okay, so this takes 1 bit and outputs 1 bit. This takes 2 bits and outputs 1 bit. And this also takes 2 and outputs 1. Okay. Now, if this is 0, it just inverts the bit. If this is 1, just changes to 0. And here, it's OR, so 0, 0 gives you 0, 0, 1 gives you 1, and all the others gives 1. And this is AND, right? So when this is 1 and 1, then this gives 1. Otherwise, it just gives 0. Now, this is an example of a circuit. Okay, so you just input your bits here and you get a bit out. I took it from some random website. It's just to give you an idea of what it looks like, a circuit. There's also another gate which you can use to do whatever you want. It's another basis. It's just an AND gate. Okay, so this is the truth table, right? It's a sort of addition modulo 2. Right? Well, not quite. It's an AND gate. It's different. This is 1 plus this 1 and 1 and 1 gives you 0. 0, 0 gives you 1, 0, 1 gives 1, and 1, 0 gives 1. Okay. And this is interesting because I took from this Tegmark book, Life 3.0, that we mentioned in the last class. This is how you could do an AND gate using physical stuff. Okay. So here's an electromagnet that you can plug to a battery. Okay. And you say that if A and B are closed, these are both bits 1. Okay. So this gives you 1, 1. And together they close the circuit here, which magnetizes this head, and it pulls the metallic port here, which transforms C into a bit 0. So the output is 0. Whereas if any one of these, if both of these are open, there's no magnetization, and this is 1. If any one of these is open, then there's no magnetization, and this is also 1. It falls down here because there's no current flowing, and then there's no magnet. Okay. You can also do that with transistors. I'm not going to go into the details, but here's the circuitry, how you would do that with a transistor. Okay. So if you can do an AND gate using these transistors and resistors, then you can do whatever you want using transistors. So the transistor is really the fundamental unit of computation. This is why we speak of transistors in usual computers, okay, as the fundamental unit of computing. Okay, the fundamental device that computes things in a computer, like the one I'm using to record this lecture. So I just brought you here some examples, also from Tegmark's book. These are some gates that you can build using the NAND gate. So you can do addition or multiplication of numbers. This is basically what's inside every calculator. Okay. So the fundamental element of classical computing is the transistor. I like to show this picture. This was the first transistor done at the Bell Labs. And for the experimental guys that are listening to me, you can think about, I mean, this looks terrible, right? It just looks unprofessional, but whatever you're doing, don't complain about the amount of material you have, because these guys won the Nobel Prize with literally this that you're looking at. So before complaining about anything, just remember the transistor image, okay? You can do it. You can do interesting, cool stuff with whatever you have now, the technology you have. Okay, you need the ideas, of course, and you need to be in the right moment, at the right time, with the right ideas, but okay, this is just motivation for you. So the more operations we can do, the more we can compute in this realm of computable functions, okay? In a realistic sense, right? Because of course these operations take time, and you can do more complex computations if you can do them faster and if you can do more of them. Okay, so you want to increase the number of transistors, right? Because with transistors you can build an AND gate, and the NAND gate can be used to compute whatever you want. So this is something which is called Moore's law, or at least a version of it. So in here you have the date, and here you have the size of the transistor in the log-log graph, right? And you see that the size of the transistor decays, okay, decreases with time, okay? And it decreases kind of in an exponential trend here, okay? So basically, we're going to reach a moment in which the transistor is, well, I mean, we're already at the moment where the transistor is nanometric in size, so you need nanotechnology to calculate things, and electrons start to tunnel around the transistor without much control. And this is really one of the problems of classical computing and making computers better, okay? So this is a recent, relatively recent image of what appears to be the smallest transistor ever made. I don't know if this is still the record. If somebody knows, please let me know. So it's 3 nanometers is the scale here. I mean, it's incredibly small, right? And the more you can have, the more you can do, okay? This is an example of a modern supercomputer. This is from Google, right? And I just want to end the class, okay? We've seen that there are limits to computation. There are functions which are uncomputable. This is quite interesting. We've seen that there is a hierarchy of problems, of computational problems, right? You can compute things in a polynomial time or in a non-polynomial time. So there's a class of problems that in practice you're never going to be able to solve, even though they belong to the realm of the computable things. So we need to go to new ideas, right? We need to think about new ways of doing computing. And this is what quantum computation is all about. This is our next topic of study. So I just want to leave you with this idea here from also from Tegmark's book. This is Moravec's landscape. So Moravec is this guy. He says, okay, computers can do some things which are now shown here as the water, okay? So the level of the water is the level of what computers can do today. Okay, so they can maybe drive a car, or they can do arithmetic or play chess, Jeopardy, and so on. And we're getting to the point really where as the sea level rises, this is Moravec's analogy, computers start to get better and better. And I mean, we feel pretty safe here on the science and art and cinematography and book writing part, but this may not be the case soon enough. Okay? And with quantum computing, the sea levels may rise even faster. Okay, so next we're gonna start looking at what quantum mechanical computers can do. Okay, now you know what a Turing machine is, you know what's a computable function, you know what algorithms are, you have basic ideas of circuit models for computation and Turing machines examples and so on and so forth. You even get some idea of complexity classes. So we're really ready. I mean, we know enough about classical computation that when I present you what a quantum computer is, you can finally start to appreciate what it means and what the quantum advantages are. So I hope I was clear. I hope everyone is safe, and see you soon. Bye-bye.